So, whenever you're designing a circuit that has an analog signal that's being measured by a microcontroller, maybe an Arduino or something along those lines, it's really important to consider the voltage range of your signal compared to the voltage range of your analog to digital converter. So something like an Atmel chip, which is on the Arduino, its typical ADC range is from 0 to positive 5 volts. So as an example, I'm making a circuit that uses this current sensing resistor, which is a very low resistance and a high wattage. So that means that it's good to have a lot of current going through it, and there won't be a lot of power loss through it. And it's also reasonably high accuracy. But since this is such a small resistance, we know from Ohm's law that the voltage across this resistor is going to be reasonably small. So we need to make sure that we utilize our full ADC range. So in order to do that, we need to bring OpAmps into the picture. OpAmps is short for operational amplifiers. And to be honest, I think that this is one of the most useful integrated circuits or integrated circuit types. There's a lot of functions that you can do with them, and they're very commonly used, mostly in signal conditioning. And the three most common things that you'll see being done with OpAmps is multiplication or division, which is applying some sort of gain to the signal. And there's also summing, which is adding multiple voltages up together. And then there's kind of a special case of the summing, which is the differential amplifier, and that's looking at the difference between two voltages. So the first one, multiply and divide, is typically when you learn about OpAmps, this is the first thing you learn about. And what that does is, if we have a small voltage, say an AC signal, that's going through our resistor that we just looked at, so this is due to current flowing through the resistor, and let's say, just to put a number on it, by small, this is maybe 0 to 0.1 volt. So this is reasonably small, and we want to scale this so it uses the entire resolution or the entire capability of our Arduino ADC. So that is 0 to 5 volts. So it's not negative, it's 0 to 5 volts. So kind of an analogy for this is, imagine you have a Jeep and you always have to drive long distances in it. And say you have a 10-gallon tank, but you only put 1 gallon in it every time you go somewhere. So you're not using the full capability of your vehicle. You could be putting 10 gallons in and going much further, but you're not. You're only putting in a small fraction. Same with your Arduino. If you know your signal is only going to be 0 to 1 or 0.1 volt, but you know your ADC is good for 0 to 5 volts, you can use an OpAmp to multiply your signal, so this signal will then turn to much bigger. It will be, well, so excuse my crude sketch, but the important thing is the amplitude will now be from 0 to 5 volts. So also, you can apply a gain that is a fractional gain, namely division. So if you have a signal that's too big and you need to go the other way, maybe you have a 10 volt signal and you need to go down to 0 to 5 volts, you can apply a gain of 1/2. But there's also an easier way to do that. You can just run it through a voltage divider. But sometimes you might need a high impedance or something along those lines, and it might be a good idea to look into using an op-amp for division. The next op-amp configuration that we want to look at is the summing configuration. And what this allows you to do is look at multiple voltages and add them together or subtract them if they're negative or what have you. And probably the most useful thing for the summing amplifier in terms of signal conditioning or getting it to fit into your ADC happily is, say you're looking at a big signal and you really want to look at it accurately in a certain range. So maybe you have a 120 volt signal. Let's say we've got a 120 volt AC signal, and let's say that we only want to look at this zone right here. So maybe we're looking for very fine inaccuracies in the voltage. So maybe you suspect that your 120 volts might be slumping down to 115. So you want to look at the top 5 volts of it. So what you can use a summing amplifier to do is to subtract this portion of the voltage, and then with the same exact amplifier you can kind of mix and match functions, so we can also multiply. And so what we'll get is a big modified voltage that will be from 0 to 5, and it will this would have previously been a much smaller voltage, and you're also getting rid of all of the voltage that you don't care about measuring. The configuration type that we're really going to focus on in this video, though, is the differential configuration. And what this is used for is when you're looking at the voltage across a component. So say we have our resistor here, and maybe, so this is our shunt, so this is our 0.0002 ohm resistor, and there's also some kind of load here, and then ground. So let's say we've got this going to just a voltage. So we can't, with our op-amp, we can't measure a voltage with reference to ground because we would be taking the voltage across this whole circuit. Instead, what we want is you want to measure the voltage just across this resistor in order for Ohm's law to work properly. So what we need, obviously, is a differential amplifier that will take the voltage at this point and it will subtract the voltage that it measures from this point. And also, just like how we did in the summing amplifier, we can apply some sort of gain to this. So as I said before, the voltage across this is going to be reasonably small, and if you want to multiply it, we have that capability. Next, I want to talk about where you actually start when you decide you want to implement one of these circuits. So all you really have to do is Google op-amp circuits, and you'll find lots and lots of different configurations. But a document that I like to reference is this National Semiconductor document that has a bunch of circuits, and National Semiconductor knows what they're talking about. So I think that this is a really decent, comprehensive reference. And it starts out with most of the ones that we just talked about. So here's our summing, the amplifier here, this is just your gain, and right here's our difference amplifier. And we have our equations here, and this is the circuit. And what we really want to look at is this right here, this V out equals R2 over R1 times V2 minus V1. So this V2 minus V1 is the difference part, and this R2 over R1, that's the multiplication part, or that's the gain. And so obviously it's referring to these resistors here. And so there's a special case that we're looking at, which normally is what you're going to want to do, is you're going to have R1 equal to R3 and R2 equal to R4. So another thing that you notice is, so this is a complete schematic in essence, and it lists a part number for the OpAmp. That's what this big triangle component is here. And when you actually go to look up OpAmps on a site like DigiKey, you'll find that there's 35,000 results. So there are a lot of different OpAmp choices. So really the most important thing that I'd suggest that you look out for is make sure that it can handle, or make sure it will work with your voltage supply that you have available. You also, another good thing to consider that I always like to pick out is I find OpAmps that are rail to rail. So what that means is, well, the OpAmp circuits, the cheaper ones, if you supply them with 5 volts, the supply line, and you want to amplify a signal, you will only be able to get up to about 4 volts, and at least 1 volt is wasted. You can think of it that way, wasted in the process of doing the amplification. But rail to rail allows you to use the full potential of your supply. So back to the circuit, let's take a look at an implementation of this. I constructed the differential amplifier circuit in a software called QUX, and that stands for Quite Unusual Circuit Simulator. It's open source, and it's still in development, but I think it's pretty great. I like that I can put my circuit and my simulation output right all at the same spot, so I don't have 1,000 windows opened up. And also I like being able to specify my simulation parameters like you do in this software. So anyway, designed exactly according to that circuit in the document we just looked at. These 4 resistors here, these set our gain, and we can actually look at it. We remember that our gain is this resistor, and well, assuming that this resistor equals this resistor and this resistor equals this one, all we have to do is look at the bottom 2, and our gain is R5 over R1, so that's 250 kiloohms over 1 kiloohm, so our gain is 250. Now, where did I find that gain from? How did I figure that's what I needed? Well, I know from Ohm's law that when I put 100 amps through this circuit here across my 0.2 milliohm resistor, I'll get 0.02 volts out. And I want this 100 amps to be the maximum range that I expect. So I want my circuit to operate from 0 to 100 amps through this resistor. So what that means is I want this 0.02 to be equal to 5 volts on the output. So it's pretty simple. I just have 0.02 multiplied by a gain equals 5. And doing a little bit of algebra tells me that my gain needs to be 250. So that's where I found my resistor values from. But there's something that you want to be wary of when you're designing specific gains, and that is that not all resistor values exist. If you go in your lab, you're probably not going to find a 250 kiloohm resistor. There are documents that exist, like this one here, that show standard resistor values, and I look for 250, and it looks like the closest I can get is 240. And I'd recommend undershooting so you don't go higher than the voltage that your ADC is good for. You want to go a little bit under just to be safe. So what we're going to do is we're going to change these to 240. And then we're going to rerun the simulation. And so right here you can see, well, the details of my simulation is I'm doing a parameter sweep. So I'm going from 0 amps from this current source all the way to 100 amps. And then my output, I'm looking at Vn, which is the differential voltage across this resistor. So this voltage minus this voltage. And I'm getting that through this equation right here. Vp, which is marked right here, minus Vn, marked right there. So I can see my input voltage to the amplification circuit. And I can also see my output, which ranges from 0 to a little less than 5 volts, but this should be acceptable. And also what I want to see is the loss due to current, and so I just calculated that by multiplying my In times my Vn. And so what that tells me is how much wattage is going to be lost due to the measurement. So when I'm at 100 amps, there will be 2 watts that will be lost across this resistor, which I've been told is not going to be too big of an issue for this application. So to further illustrate what's going on here, I also did a transient simulation, which is showing some sort of AC wave going through. So you can see my source now changed to an AC current source that's putting out 1 amp at 10 hertz, and that's across our shunt resistor. The rest of the circuit is the same. And so we look at our output here. So this blue wave is our output, and we can see that its peak is about 0.05 volts. And we look at our input, and it's very, very small. We can barely even see any fluctuation here. So that's why in this graph here you can see, so this is 200 microvolts, which is, very small, and we were multiplying it by 250 to get a wave that's much easier to work with for our circuit. So this was my quick survey in OpAmp circuits. Hopefully you've seen that they're really easy to implement actually. There's nothing that intimidating about it. The math is simple and the layout is also pretty simple. Especially when you consider the alternative, which is designing things completely out of transistors. So transistor amplifiers, the math is going to be a little bit more difficult, and the circuit layout is also considerably more difficult. So that said, I did simplify the circuit that we just looked at a little bit, and the biggest thing that I left out is the decoupling capacitors. And what those capacitors are used for is they act as a low pass filter to prevent noise from getting into the op amp and essentially destroying your signal or getting amplified to the point where your signal is no longer clean enough to measure. So if you're going to design an op amp circuit like this, I would recommend also looking into decoupling capacitors and how to properly implement them. The other last thing that I want to talk about is this op amp circuit that we just looked at, and most of the op-amp circuits you will look at assume a dual supply, meaning that you have a plus minus supply, so maybe a plus 5 volt minus 5 volt supply. But in the real world, when you build your circuit, you might have something like a 9 volt battery, and if it's just a 9 volt, you're going to have to find a way to either mimic 2 supplies, or you might only be able to use a single supply in your op amp. And all of the typical designs, they don't necessarily go out of the window, but they will have to change a bit in order for your circuit to work properly. So you might have to look into something called single supply design. Thanks for watching this video, and I hope that it was enough to give you a little bit of exposure to op amps. And the important thing is to know that they're there, and the circuits are just a Google away.